Y empezamos como ayer con la juventud. Tenemos a Juan José Mateu, Juanjo, que está terminando la tesis con nosotros aquí en la Universitat Jaume I. Él, bueno, pues es un gran investigador, ha sido graduado por la Universitat Jaume I y ha hecho el máster también en Química Aplicada y Farmacológica. Y ahora está estudiando el desarrollo de catalizadores multifuncionales y nos va a presentar pues los últimos resultados de su investigación. Pues Juanjo, cuando quieras.
Thank you, Sixte, for your kind introduction, and thank you, the members of the organization, for inviting me to give this talk. And today, I'm going to present one project, which is part of my PhD thesis, that I have entitled Unrevealing New Carbon-Carbon Coupling Pathway, Molecular Molybdenum-3 Sulfur 4 Clusters Catalyst Orchestrates Radical Generation. As most of you are familiar with multifunctional materials, material science, I'm going to talk a little bit about molybdenum disulfide. This is a well-known material that is formed by different layers that are stuck together through van der Waals interactions. And among all these applications, I would like to highlight two of them. The role of this material as semiconductor in optoelectronic devices and energy storage purposes, but also the role as catalyst. This material have been used as catalyst for different reactions, such as hydrodesulfurization processes, reduction of nitro compounds to obtain valuable amines, oxidation of sulfides to obtain sulfoxides or sulfones, and it has also been used as a catalyst in coupling reactions, such as sulfur-sulfur, carbon-nitrogen, carbon-oxygen, and more recently, carbon-carbon coupling reactions. But we focus in this last reaction. There are inherent difficulties to obtain mechanistic information about the processes, and despite there are some publications that suggest that the terminal sulfur atoms of the material are the active sites of the material, we must take into account the role of the molecular counterparts that can be used as model for the active site of the material to get more insight of the operating mechanisms. Regarding the active site of molybdenum sulfide, we found the edges and the basal planes. The edges can be mimicked by the molecular clusters of formula molybdenum-3, sulfur-13, and sulfur-7, and the units with formula molybdenum-3, sulfur-4 can be used as model for the basal planes due to their topological similarities. So in our group, we work with these three units, but nowadays we are focused on the catalytic activity of the molybdenum-3 sulfur-4 unit. This cluster can be coordinated with different terminal ligands, such as halides, pseudo-halides, hydrides, or hydroxo, but also we can decorate with different bidentate ligands, such as diphosphino, aminophosphino, diamino, diimino, or more recently, imidazolil ligands. And these clusters are active in different valuable catalytic transformations, such as formic acid decomposition, reduction of nitro and azo compounds, and more recently, the semi-hydrogenation of internal alkynes. If we focus in this last reaction, the first example was published some years ago, and we use the diamino cluster that we can observe in the slide, and we used harsh conditions, and this reaction was not selective. But this publication was very useful to demonstrate by DFT calculation the operation of an unusual sulfur center mechanism. Later on, as Maria, my colleague, mentioned yesterday, only changing the bidentate ligands by a diamino ligand that we can observe, an imidazolil amino that we can observe in the screen, we observe a complete change in the reactivity of the system, obtaining selectively the acetylstilbene under less demanding conditions. But when we try the hydrogenation of terminal alkynes using this diamino cluster, we not only observe the hydrogenation products. To our delight, we also observe several carbon-carbon coupling products. So at this point, we focus all our effort to optimize the yield of this product and its selectivity. For that purpose, we test several molybdenum 3-sulfur clusters. For example, when we tried the diphosphino and aminophosphino ligands, we didn't observe any conversion. When we tried this diamino cluster, we observed some conversion, but any product. And then we tried this tridentate amino cluster, and we observed some conversion, some semi-hydrogenation product, but any carbon-carbon coupling. So we continue all our experiments with the previous mentioned diamino cluster. Then we move to optimize the temperature and the pressure. We obtain the maximum amount of coupling products, decreasing the pressure from 20 to 10 bars of hydrogen, and we maximize the carbon-carbon coupling products, increasing the temperature from 17 to 80 degrees. Interestingly, with these conditions, we also increase the selectivity of the system, since product 2E was not observed, not detected. Then we tried some protic and aprotic solvents. Interestingly, this cluster is water-soluble, so we tried the reaction also in water. But despite some of these solvents yield some coupling products, none of them increase the results obtained with methanol. And we also tried different catalyst loading amounts, and the best results were obtained using a 5 mol% of catalyst. At this point, we realized that the same motif was repeated in almost all the products. So we wonder if this could be the result of a radical process. At this point, we add acrylonitrile, which is a trap used for carbon-center radicals, and we were amazed to observe the formation of only 2 products. One, the styrene, and this radical adduct. So in fact, this gave us some mechanistic information that is the operation of at least 2 reaction cycles, one for the generation of the styrene and one for the generation of the radical. Then we wanted to know if this was a metal or a sulfur center mechanism. So we add copper chloride to the reaction mixture to generate this Cuban type cluster that presents all the sulfur positions block. The inhibition of the catalytic activity is a clear evidence of the operation of a sulfur center mechanism. Then, taking into account the presence of hydrogenation processes using molybdenum sulfide clusters, we prepared an experiment to evidentiate the formation of sulfur hydrogen moieties. For that purpose, we add triethylamine to the reaction mixture to generate a basic medium that prevents the formation of sulfur hydrogen moieties. And again, the inhibition of the catalytic activity was a clear sign of the formation of these sulfur hydrogen moieties. Finally, we wanted to know how many sulfur hydrogen moieties are formed. And since these acidic groups can exchange hydrogen by deuterium in presence of deuterated methanol, for example, we performed the reaction using deuterated methanol, and we observed the deuterated methanol, the final product deuterated in 4 different positions. So if we take a closer look to these isotope labeling experiments, on the left side, we can see the NMR spectrum of the final product using the normal methanol, and in the right, we can use the proton spectrum of the product using deuterated methanol. If we take a closer look to the aromatic region, here and here, we don't see any difference in the signals. But if we pay attention to the aliphatic part, in this one, we can see a decrease in the integral signal due to the deuterium incorporation. So at this point, we also perform a cluster monitoring during the course of the reaction, and we observe by mass spectrometry, and we observe the coexistence of 3 species. The first one is the diamino cluster. The second one is a well-known cluster that is the dithiolene adduct, resulting from the addition of the alkyne to these bridging sulfurs. And the third one presents some similarities to the previous one described, but in the third sulfur moiety, we have the radical attached. So these 3 species coexist during the reaction until the phenylacetylene is completely consumed. And at the end of the reaction, we only see the diamino cluster. And we don't see any decomposition product to obtain a more species of lower nuclearity. And this is a sign of a cluster catalysis process. So at this point, motivated by our ongoing interest to reaction mechanisms, we try to propose a tentative pathway to describe the radical generation, taking into account all the experimental evidences that we have, that were the operation of 2 parallel cycles, one for the radical generation and the other one for the styrene generation. That this is a sulfur center mechanism, that we have generated sulfur hydrogen moieties, that we can detect some intermediates by mass spectrometry, and that this is a cluster catalysis process. That this means that at the end of the reaction, the cluster must be recovered. So we started our reaction with the hydrogenation to obtain this bis hydrosulfido intermediate 3. Then the benzylic carbon of the alkyne is attached to the third bridging sulfur. The 2 hydrogen atoms from the sulfur moieties are transferred to the terminal carbon, and then a second hydrogenation process is occurs, generating this bis hydrosulfido intermediate 5. 1 hydrogen atom is transferred to the unsaturated carbon to obtain intermediate 6, from which the radical can be released to obtain the hydrosulfido intermediate 7. This nucleophilic radical can react with the acrylonitrile through a Gibbs-type addition to obtain the radical intermediate. The radical intermediate can take the hydrogen atom from intermediate 7 through a hydrogen atom transfer processes to obtain the Gibbs adduct for A, labeled as for A, and recover the cluster species. But this Gibbs adduct can also be obtained from intermediate 6. From intermediate 6, through a hydrogen atom transfer, we obtain intermediate 8 with 2 bridging sulfurs and 1 bridging thiolate, that upon insertion of a second molecule of alkyne, we obtain intermediate 9 that we have previously detected by mass spectrometry. At this point, the radical moiety can be released, obtaining the type 1 adduct that is in constant equilibrium with the diamino cluster catalyst. So, having developed this simple and green protocol for the generation of carbon-centered radicals, we wanted to explore the synthetic utility of this protocol. For that purpose, we studied the tolerance modifying both the alkyne and the radical acceptor. For that purpose, we first test some acrylates as radical acceptors, which are broadly used in polymer industry, and re-optimize the reaction conditions to increase the yield of this cross-coupling product. So we use this series of acrylates that are used in polymer industry, and for example, the 2-ethylhexyl and butyl acrylates resulted in good radical acceptors. The system doesn't tolerate the substitution in the inner position of the alkane because the product of this metacrylate is not detected, and even though the benzyl acrylate resulted in lower yields, the final product was isolated. Then we studied the scope of the alkyne, modifying the aromatic alkyne, and using a reference the product between the phenylacetylene and the butyl acrylate. So, for example, the methylation in the para and meta positions are well tolerated, but when we use a starting material, the ortho-substituted alkyne, we observe a decrease in the final product, in the yield of the final product. We also substituted the alkyne in the para position with a phenyl ring and different halogen atoms. And for example, the final products were obtained without dehalogenation. And we also test some alkynes with electron donor groups, such as methoxo and amine. And interestingly, in this, using these alkynes, the yield of the final product was increased. In contrast, when we used electron withdrawing groups, such as trifluoromethyl and ketone, the yield of the final product decreased, which can be that, and this behavior can be explained by the role of these donor or withdrawing groups in the stabilization of the radical in the ring. Then we tried some heterocycle alkynes. For example, the orthopyridine, we couldn't detect the final product, but when we moved to the metapyridine, we detect the final product with low yields. And for example, when we use the 3-ethinylthiophene, the final product was obtaining good yields. Then we wondered if it was really necessary to have a conjugated group attached to the alkyne. So we tried a couple of non-conjugated alkynes. And unfortunately, the final product was not detected. But when we tried the simplest enine, cyclic enine, that has this group conjugated to the alkyne, we detect the final product. So this was a clear evidence of the requirement of a conjugated group that stabilize the radical intermediates generated during the process. So now I would like to conclude giving some general remarks that we have reported the first protocol of generation of a carbon-centered radical using molybdenum-3 sulfur-4 cluster as catalyst without additives and using hydrogen as reductant. And this means that any subproduct is generated, that the use of inexpensive starting materials such as acrylates and terminal alkynes makes this protocol appealing for the generation of fine chemicals. And last but not least, we have reported a new cluster catalysis process that is based on a sulfur center mechanism based of experimental evidences. Finally, I would like to thank the members of Molecular Materials and Theoretical and Computational Chemistry Group, our collaborators at Leibniz Institute for Catalysis, and the funding agencies to help us to develop this project. Thank you.
Bien, muchas gracias, Juanjo, por la exposición. Ahora tenemos tiempo para algunas preguntas. ¿No? Todavía estamos un poco dormidos. Pero una pregunta.
Juanjo, una pregunta. Sé que habéis hecho cálculos teóricos para entender y calcular los caminos de reacción y las barreras. Entonces, la pregunta sería, en todo el ciclo que has mostrado hoy, ¿habéis encontrado cuál es la etapa limitante de la velocidad de la reacción?
Los cálculos que hemos hecho no han sido con ese ciclo. Estábamos haciendo otro ciclo y cuando nos dimos cuenta que las barreras eran imposibles, decidimos dejar los cálculos y utilizar otro mecanismo en base a otros mecanismos que están publicados en el grupo, que son, por ejemplo, el de María, que explicó ayer, que es la hidrogenación primero y después la adición del... Aunque no sabemos cuáles son las barreras de este ciclo.
¿Alguna pregunta más? No, pues agradecemos otra vez a
Gracias.
Juanjo.